I want to show you guys that I made a small change to the homepage because it was annoying me. And if it was annoying me, maybe it was annoying you too. I am now minimizing that schedule. You can still click on it, so anytime you're curious about when is our first unit test next weekend, when is our midterm, March 5th, you can always just make it bigger, but this gives you quicker access to these links. And it was annoying me that I had to scroll past that schedule every time to get to the links. So I've got another worksheet for when we finish the one from Tuesday, and that new worksheet has been uploaded, Stereochemistry and Reactions. I probably should have called it Terminology and Reactions, to be honest. And then I hope, sorry, you can't see this very well. I have another worksheet that I had made last semester. Those of you that had my OChem 1 know that I was in the process of kind of learning how to develop worksheets last semester, and I did that after Unit 1. So this was what I had tried to put together for Unit 1, but we didn't go through it. This is really just practice problems. I don't have a key for it, so if you want to see whether you've got them right or not, just send me what you get, and I'm happy to check them over for you. Or maybe I'll have one of you try and make a key for it, and then I'll keep it and upload it. So if you want to practice the reactions that we're going to do, this is a good resource for you. But the worksheet that I'll be handing out in a little bit has these maps to help us lay out all of the reactions that I want you to have good foundations on. And you guys that were in my OChem 1 know that sometimes I overload those reaction diagrams, and so you might have noticed I'm trying to spread them out, and we're going to see if spreading out the reactions a little bit more gives us more space to keep things more organized. Let's wrap up Cario. We had gotten as far as resonance, is that right? Oh, that scared the living daylights out of me. We'd said that increased resonance means increased stability. Increased resonance in the conjugate base means increased in the conjugate base or conjugate acid means increased stability. Less likely to go in reverse. So we're looking at this far right-hand column when considering this. I gave you guys an example on Tuesday of acetic acid becoming protonated and how one of the oxygens gets protonated and has resonance in the conjugate acid. One of the oxygens gets protonated and has no resonance that stabilizes it. Here, the problems that we're looking at, we're not looking at the conjugate acid. Instead, we're going to look at the conjugate bases. So we're going to deprotonate each of these. Our top structure in the top right is acetone. When acetone gets deprotonated, it's one of the carbons on either side that loses the hydrogen. The second compound is toluene. And when toluene gets deprotonated, it's that methyl group that will lose the proton. And then the last compound is trans-butene. And we're going to look at, again, one of the methyl groups on the sides losing the hydrogens. So these are the conjugate bases. And now the question is, how much resonance can we predict? Remember the 3-atom rule. Identify a pi bond. That's 2 of your 3 atoms. And then identify somewhere that has a charge or a lone pair. In the top structure, we've got a pi bond between C and O. And then a third atom adjacent to that, the carbon, has a lone pair and a charge. And I'm sorry, I didn't bring my worksheets, but yeah, good. So here's my 3 atoms. In the resonance form that I'm going to draw, the pi bond should shift, and the charge should relocate from atom 1 to atom 3. So, some practice on arrow pushing as well as we do these resonance structures. Electron arrows show electrons moving from high density to low density. High density here is the negative charge, and electron pairs are really only able to move one atom distance. So since this carbon has the electron pair, it can share it, but it cannot lose it. It's not going to toss it anywhere. When this pi bond breaks, it can either break to the carbon of the pi bond or to the oxygen of the pi bond. And in this case, oxygen is more electronegative, so oxygen owns those electrons, and the arrow breaks up. Here is my conjugate base in a different resonance form. When we look at the conjugate base of toluene, I've got that carbon 1 with the negative charge, and then carbons 2 and 3 have a pi bond. I have to choose one of the routes in the ring rather than the other because that's just where my pi bond is drawn. I can show an arrow pushing the lone pair in, and then an arrow pushing the lone pair out. This relocates my double bond. It relocates my lone pair. Now we look for another set of 3 atoms. 1, 2, 3. My pi bond shifts within the ring, and my negative charge shifts within the ring. Now I look for another set of 3 atoms. And one more time, I get a new pi bond location within the ring and a new negative charge location within the ring. Question. The second and fourth resonance forms are related by flipping the molecule over like a pancake. Does that mean that only one of those forms qualifies as contributing to resonance? Or do they both contribute to resonance? Why?
It doesn't make sense only one would contribute. I don't know.
Would you agree they're essentially identical? The position of the pi bonds, the relation of the charge to the position of the pi bonds, identical. So identical, in fact, that I could, just by manipulating the structure a little bit, rotate it and get them to superimpose. They're identical. They are identical. And yet they're distinct because there are 2 places along the ring that it can show up. So both contribute despite the fact that they are identical. That's not bad, that's great. Awesome. Last one, how many resonance forms can I draw?
1.
Just 1. Pi bond, I'll show this. The lone pair moves in to form a pi bond. The pi bond breaks to move out. That's the only resonance form I can get. So I gave you this rule that with resonance, increased resonance forms increases stability. But that's not always true because there are other contributing factors like the atom that the charge is being held on. If a carbon holds a negative charge, it's not as stable as when an oxygen holds a negative charge. So I'd like you guys to discuss which of these resonance forms, which of these conjugate bases, which have different numbers of resonance forms and different atoms involved, which of these conjugate bases do you think is the most stable? And in other words, which of the conjugate acids do you think is the most acidic? The most acidic acid will generate the most stable conjugate base. Discuss this with yourselves for about a minute or two and see if you can decide which of these is the most stable. All right, what did you decide? First one is the most stable. Acetone is the most acidic. Any others? Toluene in the middle. Disagreements? So what did you lean into, Elliot?
I was leaning into the oxygen because it's the most electronegative, so when it's charged. But I think Ian was thinking the middle one because it has the most possible resonance.
Sure. Katie?
Well, we were just talking about like aromatic rings are really stable structures. So that's kind of what the stability aspect is.
Sure, the stability of the aromatic ring maybe contributes to the stability of the base. I like that train of thought. I want to show you guys a resource that you can use when you want to review acidity. It's not on class resources, so sorry. That's where it should be. Maybe I screwed up and oh, sorry, it's under useful tools. These are tools that I used to have on my homepage, but now I've got them buried in here so far that I can't even find them. I've got this document with functional groups and pKa's, and you could come in here and, in theory, find some of these examples to look for the pKa's that they give. What we see is that something like the top structure, acetone, has a pKa between 15 and 25. We actually don't see great examples here for the other two, because these other two are not just sp3 hybridized carbons. They're sp3 hybridized carbons adjacent to a carbon-carbon double bond. And that's something that we don't have exemplified in here. But if we see the sp3 hybridized carbon is at the very bottom, and the sp3 carbon next to the CO double bond is in the middle, then we might reasonably be able to argue that the other two next to carbon-carbon double bonds lie somewhere in between here, given the fact that oxygen is more electronegative. So if the conjugate base can delocalize the lone pair from one carbon to another, does that stabilize it better or worse than delocalizing it across 4 carbons? Well, more positions, that negative charge is now delocalized more. This is more like a negative 1/2 charge, negative 1/2 charge. This behaves more like a negative 1/4 charge. So this is more stable due to increased resonance. But delocalizing that negative charge onto an oxygen, because of the electronegativity, means the oxygen holds it better. This actually goes back, it compounds resonance with the atom effect. What's a better acid, carbon or oxygen? Oxygen is a better acid. So what's a more stable conjugate base, carbon with a negative charge or oxygen with a negative charge? Oxygen with a negative charge is more stable. So despite having less resonance, it has that compounding effect with the atom and the electronegativity, giving us our most stable conjugate base on top, followed by our second most stable conjugate base, and then our least stable conjugate base. It does get confusing, doesn't it? You can't just count the resonance forms. So when I assess you on these types of questions, I'm typically not asking, I'm not trying to trick you. I'm not looking to see if I can come up with the most convoluted way that all of these rules impact each other. But I do want you to be aware that they impact each other. Deal? Yes.
Can you I'm confused on the relationship of most stable base to strongest acid or how it works. Can you explain?
We will. Actually, when we get to equilibrium, which is right after we finish Careo,
Okay.
we'll talk more about why is the strongest base the most stable acid? Why is the strongest acid the most stable base? So when we get into equilibrium, I'll try to help you understand better this relationship between the conjugates.
Okay.
Elliot.
So just to triple check, the top structure is the most acidic.
The top structure, because I pulled it off now. Yes, the top structure, acetone, is the most acidic. That structure up there is the most stable base. When using resonance as a way of predicting acidity or basicity, you should assess the resonance of the conjugate, which is Ella's question. How can I assess the conjugate and then pull it backwards to understand the thing I want to in the first place? And that's where I think equilibrium will help us understand it better.
Because I would think that the one that has more resonance forms would be the more stable base.
Right, so we would think that this should be the most stable because it has the most forms. But every single form places the negative charge on carbon.
Which isn't
Correct. It's more favorable to place that negative charge on oxygen, even if it has less resonance forms. All right. So remember, we're going through Careo. And our next component of Careo is induction. Lily?
Sorry, I was just wondering, with that top one, what if that was a bromine?
Yeah, it changes the game a lot.
Okay.
And we'll come back to that in our last unit this semester.
Okay.
Which actually kind of gets into this idea of induction. Induction is both a push and a pull effect on electrons. So induction has two different things. I would say most of the time you see questions that talk about inductive pull and less about inductive push, but we're going to talk about both this semester. This one I find to be the hardest to summarize in that short little snippet like I've been doing all the others. If we have more electronegative atoms, then we tend to have a more acidic hydrogen. The presence of electronegative atoms increases acidity. For this problem, by the way, we're doing the second to the right column, the various acetic acid groups. Acetic acid followed by bromoacetic acid followed by trifluoroacetic acid. The acidic hydrogen is the one attached to the oxygen. Oxygen in general is a good acid. A better acid than carbon for sure. Again, we can think about the conjugate base and how these electronegative atoms stabilize the conjugate base. Before we get there, what we can say is that a CH3 group does not hold on to its electrons all of that well. It's willing to share electrons. So this CH3 group has an inductive push. It actually pushes electron density towards that carboxylic acid group. A bromine, being electronegative, has a pull towards itself, meaning it's trying to pull electrons away from the carboxylic acid group. Fluorine, being the most electronegative and having three of them, creates this very strong pull from that carboxylic acid group. Okay, what is a carboxylic acid group to do if it has groups pulling on its electron density? Well, it may give up a hydrogen ion, accept that bonding pair of electrons back, and allow that new excess electron density to be pulled out by the electronegative atoms. So we look at the conjugate bases, and we see that this negative charge on O is being pulled towards the fluorines. That makes it less likely for that negative charge to go back and grab another hydrogen ion and act as a base. Strong acid because it has a weak conjugate base. With acetate, on the other hand, the conjugate base of acetic acid, again, this methyl group is actually willing to donate its electrons, push its electrons towards that O- group. What does an O- group want to do if it has extra electron density pushing on it? It already has an excess of electrons. It's getting more electron density pushing on it. It's more likely to act as a base, to take another hydrogen, which means it's less likely to act as an acid in the first place. Least acidic, strongest conjugate base. Most acidic, weakest conjugate base. So again, we typically say it as increasing electronegative atoms increases acidity. But the other way to look at this is increasing electropositive atoms, like these carbon groups, alkyl groups, increases basicity. We'll be exploring this again more this semester. All right, the last factor in acidity is orbitals. The more S character in the orbital, the more acidic that atom is, the more willing that atom is to release its hydrogens. So an sp orbital is more acidic than sp2 orbitals, which is more acidic than sp3 orbitals. Sp is 50% S. That's the most S character it can have. Sp3 is 1/4 S. That's the least S character it will have. So I want you guys to now do the far left column. We'll compare pyridine with this cyclic amine with acetylnitrile, CH3CN. Here's the first question. Are you able to identify their hybridizations? Who can tell me the hybridization of my first nitrogen on the left? Lily agrees. You guys agree? How'd you get there, Elliot? 3 electron regions, SPP, sp2. My second nitrogen atom? sp3. And my last one? sp. You guys are catching on to the fact that the lone pairs are assumed, but the lone pairs are still there and count as an electron region. We said this first nitrogen has 3 electron regions: single bond, double bond, lone pair. Same with this second nitrogen: single, 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 and lone pair. Can we assess these atoms by acidity? Can I rank these from most acidic nitrogen to least acidic nitrogen? Why?
Because like a half S, like one
Yeah.
and then a 1/3 and 1/4.
But where will the hydrogen come from? Can this nitrogen be an acid? What's our definition for acid? Hydrogen ion donor. And this nitrogen has no hydrogen connected to it, so it can't donate a hydrogen ion. This has a hydrogen that it can donate, so this can be acidic. This nitrogen has no hydrogen connected to it either. So rather than ranking these by acidity, only one of them can be an acid, the other two nitrogens can't even be acids, let's rank these by basicity. Let's rank these by the strongest base. That means you're going to have to flip how you think about that rule at the top. Which of these is most likely to accept a hydrogen ion? Which of these is less likely to accept a hydrogen ion? Debate amongst yourselves. Take 2 minutes on this and we'll go through the answer. I know, it's a trippy one. Katie, would you agree that if you decrease S nature, you decrease acidity?
Yes. So that would increase. Okay.
Because it can't decrease S nature
Yeah.
to decrease acidity and decrease basicity, right?
Yeah.
What are you guys thinking? Being the most basic?
Yeah.
Why? So you guys have a disagreement? Or did she sway you? That's right. Takes the hydrogen the most.
Is most basic the worst acid? Because there's a low temperature and it would want to fill.
All of them have a lone pair.
So would we just base it off of the S orbitals and go with the one that's sp3 because that's like the most, that would make it the most basic.
Does it? We know sp3 makes it the least acidic. That's what our rule up there says.
You said the flip it, right?
Yeah, and you got to be careful how you flip it. All right. Who says the sp nitrogen is the most basic? Yeah, one group up here. Who says the sp2 nitrogen is the most basic? Could we agree that it really shouldn't be the one in the middle? Like it should really either be sp or sp3 will be the ends of the spectrum. sp2 is going to be the middle basic or acidic one. Deal? That, because it's right in the middle in terms of S character. All right, so then who says sp3 is the most basic? Okay, we're pretty torn throughout the room, right? One way that we can try to navigate this problem is to look at the conjugate acids and apply the rule that we already have about how orbitals and acidity applies. That's what we did with the conjugate bases to decide acidity using resonance. We figured out which was the best acid by looking at the resonance forms in the conjugate base. So let's decide which of these is the best base by looking at the conjugate acids and then applying our rules. So the conjugate acid of pyridine is called pyridinium. I think a lot of organic chemists would probably shame me for not knowing that six-membered cyclic amine. It has a name. I don't know what it is, though. It's not pyrrole. I think pyrrole is a five-membered ring. Anyways, we've got our protonated cyclic amine, and then now we've got our protonated SP, our protonated nitrile. Now we can apply our rule. Is that correct? Whatever has the most S character is the most acidic. Which of these conjugate acids is the most acidic? The one with the most S character? The far right. The one on the far right must be the most acidic because it has the most S character. It's SP. Meaning this must be the worst base because its conjugate acid is the most acidic. Do you agree? The most acidic conjugate acid tells us the least basic conjugate base. Which of these is the least acidic conjugate acid? The sp3 in the middle, here. Our sp3 nitrogen is the least acidic because it has the least S character, 1/4 S, meaning its conjugate base must be the best base. It's such a good base that its conjugate acid doesn't give away its proton all that readily. Okay, the other way that you can approach this, rather than looking at the conjugates and applying the rule, is that you can try to flip the rule, but you've got to be careful. If it's true that increasing S character increases acidity, then decreasing S character must decrease acidity. And decreasing S character would then increase basicity. If you tried to just flip it directly and say decreasing S decreases basicity, you've kind of like made two wrong turns, yeah? Or you can flip the sign, decrease S nature, and then flip the characteristic you're considering. Decreasing S nature increases basicity. Most basic. Most acidic. All right. I want to spend a little bit of time on equilibrium, which is really what all acid-base characterization is. And I wanted to point out that equilibrium uses two one-way arrows, which is to say that equilibrium takes products and reactants and turns them into reactants and products. These are energy diagrams that are able to go forward and backwards. I want to take sulfuric acid and react it with methanol and consider the equilibrium product of bisulfate and the methylammonium ion. Protonated methanol. This is equilibrium. As sulfuric acid runs into methanol, sulfuric acid donates a hydrogen, methanol accepts it. But as the methylammonium ion runs into bisulfate, the methylammonium can donate a hydrogen ion and bisulfate can accept it. So these reactions can go forward and backwards. I'm going to pull up this tool again that gives pKa tables, pKa values. And I want us to consider which way the equilibrium lies. At any given time, is there more of the reactants on the left present, or is there more of reactants on the right present, or is it roughly 50-50? Sulfuric acid sits at the top of our table. It has a pKa of -10. Methylammonium is not listed on my table. So we'll have to use something similar to a protonated alcohol. And we have something that is similar to a protonated alcohol, and that is protonated water, hydronium. I like to say that water is inorganic alcohol. There's no carbon in it, but it has very similar chemical characteristics to alcohols. So we can say that the pKa of methylammonium is about -3. Can you tell me which acid is better at being an acid? How do you know? Lower pKa, and I like to say more negative. A more negative pKa, more acidic. And that's because of the equation that Ka is. You guys won't need to use that acid dissociation constant equation at all. But if you have a larger numerator, meaning more products formed, then you're going to get a number larger than 1. And if you take negative the log of that, which is what P is, then you're going to get a number smaller than 0, more negative. All right, so sulfuric acid, more negative pKa, stronger acid. Methylammonium, weaker acid. Which side of this equation is favored by equilibrium? The forward reaction. The right-hand side is favored. At any given time, there is more of these products present than there is reactants in the solution. And we can actually gauge what that difference is by taking the difference in their pKa's. So the difference here is an order of 10 to the 7 favoring the products. Again, sorry, that's a lot of information. we're not going to get into it a lot, but I do want to kind of point out the larger the difference in their pKa's, and because P is a logarithmic scale, we're using powers of 10, then the difference in equilibrium is that there is 10 to the 7 times more products than reactants at any given time. So it's a big difference. Let me say that another way. For every 1 molecule of sulfuric acid, there are 10 million molecules of bisulfate. For every 1 molecule of methanol, there are 10 million molecules of protonated methanol. Okay, let's do another one. Let's take this terminal alkyne and let's react it with hydroxide and consider the equilibrium with the deprotonated alkyne and the water. I'd like you guys to decide what is the acid on both sides of the equation And what are the pKa's that should be assigned to them? I'm going to scroll down so you can use this tool. What are the acids? What are their pKa's? And what side is favored by equilibrium? Not -2. You were looking at what we had above, but that was the pKa of H3O plus. So you decided this is the acid here? No? It donates its hydrogen, it loses it, right?
Yeah. No, yes.
What about in the reverse reaction? Which of these is the acid in the reverse?
The water.
And do you know the pKa for it?
No, I was just looking at
You're going to Google it? Oh, use that resource.
I can't really see it.
I wish I could,
Oh, it's okay. I can pull it up on my phone.
I wish I could get this out of the way. Yeah, you're right. I'll put it up there. There you go, Camille. It's probably still not perfect. What is my acid in the forward direction? 1-butyne or hydroxide? 1-butyne. We can see that 1-butyne loses its hydrogen, so it must be the acid. What's the pKa of an alkyne? About 25. What is my acid in the reverse direction? H2O, because we see H2O loses a hydrogen. What's the pKa of H2O? Who said negative what? -3. On our table, we actually saw the pKa of H3O plus was -3. When H3O plus gives away a hydrogen and becomes H2O, that's done with a pKa of -3. But when H2O gives away a hydrogen and becomes OH minus, that is closer to the pKa of just a normal alcohol. Remember, water is basically just inorganic alcohol. So I think most tables will report water as being about 15.6, but in the same range here. So in the mid-teens, 15 to 18, which is a good enough range for us to say which of these is the better acid. Water is a better acid because it has a more negative pKa. Its pKa is not negative, but it's more negative than 25, yeah? So if this is better at being an acid, it means it doesn't exist. If it's better at being an acid, this exists more. So this side is favored by equilibrium. And again, we can take the difference in the pKa values to predict what that difference in equilibrium will be. And it's about 10 to the 10. So for every molecule of water or deprotonated alkyne, there are 10 billion molecules of those chemicals in their other form. This is to say, if you wanted to deprotonate an alkyne, hydroxide is not the chemical to do it. Because only 1 out of every 10 billion molecules will get deprotonated. If you want to deprotonate it, you need to find something whose conjugate acid is a worse acid than alkyne. What would that be? Well, the conjugate base of an amine would be a worse, I'm saying this backwards. An amine is a worse acid than an alkyne, so using the conjugate base of an amine would work great. Hydride would work great, or any carbon other than that alkyne would work great in deprotonating your alkyne. The other thing about this equilibrium is that sometimes it is 50-50. It can be very close to acidity on both sides, which means you risk this chance of reactions just staying incomplete. You'll never get 100% conversion in your reaction because there's always that chance of a reverse equilibrium. All right, I want to touch on resonance before we go into our break. And we've already talked about resonance, so I think I should have done this earlier. But I want to review the rules for resonance. We'll be drawing a lot of resonance this semester, so it's important that you know how to draw resonance and how to rank resonance forms. So a precursor I want to give in regards to drawing resonance forms and using electron arrows. When you use electron arrows to show a bond breaking, bonds break toward the more electronegative atom. That is the atom that owns the electrons. So if the electrons are going to move somewhere, they're going to be controlled by the more electronegative atom. If you're going to use electron arrows to show a bond forming, those electrons come from the more electronegative atom. Less electronegative atoms are willing to accept electrons, but they typically don't have control over the electrons. It's more electronegative atoms that have the control over electrons and decide whether they are used to form a bond or break a bond. So when you show, and I know those of you that haven't had me before, you may not have the same skills in using arrow pushing, which is why I want to give you this tip. When you show bonds breaking, you will show it breaking towards the more electronegative atom. When you show a bond forming, it should always have the electrons coming from the more electronegative atom. The more electronegative atom decides what happens with electrons. All right, so look for that when we do these resonance rules. Can someone define resonance? Ooh, I like that what you added in there. Resonance is stabilizing electrons by distributing them across atoms. Anything you guys want to add to that? Stabilizing a charge. Anything else? They involve pi bonds? Yeah, you need a pi bond involved. And actually, that's what we could clarify about the type of electrons. It's not just all electrons being stabilized, but it's pi electrons. So this is movement / delocalization, depending on whether you're looking at valence bond theory or MO theory. It's the movement or delocalization of pi electrons, and it is a stabilizing force. So we'll talk a lot about resonance stabilization. That's the big feature that resonance gives us. Rule number 1 about resonance: minimize charge. Your first priority in drawing the best resonance form, the major contributor, the most stable resonance form, is to minimize the charge. So I think some of you guys and some of my OChem 1 class was asking me why thionyl chloride, which we looked at last week, has this resonance form on the right as its preferred resonance form, rather than the resonance form on the left. On the right, we break the octet of sulfur. On the left, we don't break the octet of sulfur. So what's the difference between the two? Formal charge. On the left, oxygen holds a negative charge, sulfur holds a positive. This has two formal charges. On the right, there is no formal charge. So we say that this is a major contributor to the molecule. And by major contributor, what we mean is Lewis structures don't exist. Instead, they help us model what the molecule kind of looks like. And so this model resembles the molecular orbitals better. This contributes more to the nature of the molecule than this does. Just for context, in an organic molecule, we can say something very similar with carbonyls. We can often draw carbonyls in two resonance forms, but only one of them is a major resonance form. Which of these two is the major contributor? On the left. The right-hand form tells us something. It tells us oxygen holds the negative charge, carbon holds the positive, oxygen is partial negative, carbon is partial positive. And these are the electron arrows that we would use. If I wanted to show thionyl chloride going from the left to the right, I would show the more electronegative atom forming that bond with the less electronegative atom. For my carbonyl, if I wanted to show breaking the bond, I would show the more electronegative atom taking the electrons away from the less electronegative atom. But this is our major contributor. This just helps us understand partial charges on this major contributor. Rule number 2, who remembers? Some of you have heard this 3 times. Those of you that took my Gen Chem class. One more time. Less carbon positive? Not quite. Maximizing octets. Yvonne, you agree? We want to maximize octets. Rule number 2. Now you're not far, because in the fall I told you guys that this often just shows up as carbon getting as many bonds as possible. It's rare that carbon actually, it's rare for any other atom to be missing an octet in a resonance form besides carbon. Oxygen almost always has an octet. Nitrogen almost always has an octet. Our halogens almost always have an octet. So another way of saying maximize octets is really to say, make sure that carbon has an octet. Maximize octets on carbons, because everything else typically has its octets. So I want to give you guys two examples here of how we can maximize an octet. No, sorry, first I'll do this. First I'll do this. Let's say that I have this OH group, this alcohol, and I have a positive charge on my carbon. I can show a resonance form. By the way, I didn't point this out. Did you notice the resonance arrow is different than the equilibrium arrow? This is a double-headed arrow, not a two-directional arrow. Oxygen, the more electronegative atom, can form a bond with carbon. And now I have maximized octets. Carbon on the left does not have an octet. Carbon on the right does have an octet. Oxygen kept an octet in both states. This pattern of atoms adjacent to each other sharing electrons, it is one that we'll see. But another common pattern is to see this happen over a longer scale. Once again, the oxygen here can share its electrons with the carbon and move the pi bond across. The carbon on the right-hand side does not have an octet. And in this new resonance form, it does have an octet. Now you may be wondering about these major contributors on the right-hand side. And you may be concerned about the fact that oxygen is holding the positive charge instead of carbon. Because earlier today we were talking about resonance, and we said placing a negative charge on oxygen is better than placing it on carbon. So why is placing a positive charge on oxygen better than placing a positive charge on carbon? And that's because our third rule is what I call appropriate charge placement. This is the last thing that we consider. We don't consider whether the charge should be on oxygen or carbon when we're deciding to maximize octets. We maximize octets first, and then we look for where charges can be placed. All right, I'm going to give you guys this small molecule, but for now it will do a good job of identifying our rule of appropriate charge placement. This first resonance form places a positive charge on nitrogen. But there is a 3-atom system here. The oxygen, the carbon, and the nitrogen. Oxygen can share electrons with the carbon to make a double bond. Nitrogen, being more electronegative than carbon, can take the electrons away from the pi bond. My second resonance form has a neutral nitrogen but a positively charged oxygen. Where has the charge been placed appropriately? It depends on the charge, doesn't it? In this case, a positive charge is more appropriate on a less electronegative atom. Left or right? What's the major contributor? Left. Nitrogen is less electronegative, so it's more appropriate to have nitrogen hold the positive charge. All right, another example. Let's switch up the charges this time. Here, oxygen has a negative charge. It can use that negative charge to form a double bond, break the pi bond between carbon and nitrogen to the nitrogen. Now I have a form where nitrogen holds the negative charge. What's more appropriate? The one on the left? Why? It's not just more electronegative, it's the negative charge on the more electronegative. In fact, this is something I have students come back to a lot throughout the semester. They'll say, I thought appropriate charge placement was put the charge on the more electronegative. It's not, is it? It's placing the charge appropriately. If it's more negative, put the negative on the more electronegative atom. If it's a positive, place the positive on the less electronegative atom. Notice though that when the positive is on carbon, that breaks an octet. And that's a completely different rule. So it's not more stable to give carbon the positive, even though carbon is the least electronegative out of oxygen, nitrogen, and carbon. Carbon taking a positive is not appropriate charge placement. That's breaking an octet. So first, minimize charge. Second, maximize octets, maximize bonds to carbon. Then figure out how to place the charge appropriately. All right, let's take a break. Let's come back just after the 10. And I'm going to hand out this worksheet for us to keep reviewing material on. Nothing. It's just taking much longer than I always mean to. Because it's so fun. Thank you. Whoa. You're welcome. Here you go, guys. You're welcome. I like the hexagonal paper. Yeah. Nice. Works great for drawing stuff like that.
And the hand saved and accidentally twisted on his fingers. I found the fingers in the trap. You might want to yeah, you're right. He's like, yeah, actually, like, I just see this. See, I could not. Yeah. Primary care is fine, but it's just. Do you work at the year? Technically, I guess. Yes. I work in research park, so it's like on campus, yeah. Okay. Yeah.
How much when you students probably summers. That's exciting. It's also very next week.
Yeah, I've been studying a lot.
Amazing grade.
Yes.
It's short.
There's just so much content. So it's very intimidating. But the see the doctor. Usually so get like a relationship and then just want to he's very invested in my Ben, I'm coming straight from work. This is how it goes. You're like, okay, let me off and then I'll go dress nice. I do leave early on the days I can because otherwise I'm there until like 5:30. Oh. Do you work 12? I do 4 times. Okay.
I think that works too.
Really? If I could do 3 12s instead, I probably would. I like 4 10s, but I would never want to do 5 8s.
I would way rather do that.
Would you rather do 5 8s? I like 10 4 10s.
You look like you had a question.
I do have a question. I'm trying to figure out how I'm gonna get to rave tonight.
Yeah, these are the important questions in life, really.
Yeah. Lecture-wise, I'm good.
Lucky you.
Yeah, it's very chill. It's called hug house. They're more and more expensive.
All right. Ready? We've got some terminology I want to review with you guys and make sure we're all on the same page with it. First, can we define a chiral carbon? Four unique groups. In OChem 1, a lot of students are confronted with this idea and they think it must be 4 distinct atoms, 4 distinct elements. Not true. You can have carbon chains on either side of a chiral carbon. In fact, you can have 4 carbon chains coming off of a carbon, and as long as those 4 carbon chains are unique from each other, methyl, ethyl, propyl, butyl, it's now a chiral carbon. Granted, most of the time there's hetero atoms involved. Okay, chiral carbon has 4 distinct groups. It's not necessarily true. There are some chiral centers that actually only have 2 groups, but they're a small fraction of it. The other words that we can use in place of chiral, asymmetric. Asymmetric carbons, they lack a plane of symmetry. There is no reflection between those 4 groups because all 4 groups are different from each other. I don't think I'm going to have you guys do absolute configurations this semester. Do you remember absolute configurations? R and S. And we use the Kahn-Ingold pre-log rules to decide them. I always like to give this analogy in my OChem 1 class, so some of you guys might remember this. What hand have I just drawn on the board? Why? Because you saw me do it. Okay, so you're telling me that this is definitely not my right hand? Oh, because it works, doesn't it? How do you know whether that is my left or my right hand? By the way, do you know what chiral means? It means handedness. The idea for asymmetry came from your hands. So I'm going to do this in my OChem 1 class. I'm going to give them the prompt, derive a system of rules that helps you distinguish your right hand from your left hand. I kind of talk about this in my OChem 1 class typically, but I'm going to give them the rule rather than giving it to them, have them develop it. But the idea is you need to decide what orientation your palm should be and then communicate about the relationship between your fingers. So if your palm is toward the board and your fingers go thumb to pinky counterclockwise, that's your right hand. If your palm is toward the board and your fingers go thumb to pinky counterclockwise, that's your left hand. You need to have an agreed upon orientation of these groups. With chiral carbons, what we say is prioritize the groups 1 through 4 based on their highest atomic mass at the first atom of difference. You look down those chains in those chiral carbons until you find something different and you prioritize the groups at that point. Place the lowest priority away from your perspective. Look at the 3 highest priorities. And we say that if the 3 highest priorities are 1 to 3 clockwise, that's an R configuration. And if they are 1 to 3 counterclockwise, it's an S configuration. We're just not going to deal a lot with chirality. Well, to be fair, chirality never goes away. We're just not going to focus on it as much because we have so many other fun things to look at this semester. You guys might have noticed in OChem 1 as well, when we started getting into reactions, it was like, oh, an achiral starting material produced enantiomer products. The end. We didn't go into it, right? We just said these are the 2 stereoisomers that form. If you become an organic chemist, that can be incredibly important. If you become a pharmacist, that can be incredibly important. Whether a molecule is the combination of R and S centers changes the way that it impacts with the chiral receptors in your body. For example, methamphetamine has 1 chiral center, highly addictive. Its enantiomer is the active ingredient in Vicks Vapor Rub. It's a nasal dilator. Okay, well, don't give me the one that's going to get me addicted when I'm trying to open up my nasal passages, right? So chirality is incredibly important. It's just narrowing down between isolating this enantiomer or that enantiomer is beyond the scope of this course. So we're just going to look at a variety of reactions. We're not going to look at how you selectively isolate specific isomers. Good review? Great, let's move on. Chiral molecules. How could you define one? Sarah?
Well, I don't know. No plane of symmetry. I don't know if that's for both.
Perfect. Because it's chiral, it has no plane of symmetry. Anything you guys want to add to that? Has at least one chiral center. So I like to say they have greater than or equal to 1 chiral center and 0 planes of symmetry. There are some other descriptors that go along with chirality. Meso describes a compound that has 2 or more chiral centers and at least 1 plane of symmetry. Somebody looked up what meso meant, but I already forgot. I think it meant middle. I think it means something about that plane of symmetry reflecting the 2 chiral centers.
Yeah, it means middle or intermediate.
Okay. So a meso compound has chiral centers but is asymmetric. One of the examples that we go over a lot in OChem 1 are these kind of meso compounds, which don't look like they have a plane of symmetry as they're drawn. But if you rotate this by 60 degrees, then you can see that these chiral centers actually are symmetric to each other in a different configuration. Meso compounds only need to have a plane of symmetry in at least one of the possible configurations. What's the other term that we can use to describe chirality? There's chiral, meso, and the other category? achiral. Now, to be fair, meso compounds are achiral because they are symmetric. But things that are strictly achiral have 0 chiral centers. And, of course, at least one plane of symmetry. Questions on the review of that terminology? Good? Let me ask you this. Do you need to know the absolute configuration of a chiral center to know that it is chiral? No. Do you need to know the wedge or dash? Do you need to have that stereochemistry to be able to determine whether it's R or S, a chiral center? Yes, because if you can't orient the fourth group back, you can't determine rotation 1 to 3. So without wedges and dashes, you cannot know the absolute configuration. So I want you guys to do that top row of molecules. I want you to find compounds that are chiral, achiral, and meso. Or, sorry, label these molecules as chiral, achiral, or meso. Just the top row. Sorry.
This one can't be. It doesn't have 4 different groups. This one's chiral.
Great. Yes.
So an achiral doesn't have a plane of symmetry.
Achiral does have a plane of symmetry.
So where's the plane of symmetry in this?
The plane of the paper. Planar, sp2 carbon, trigonal planar. Planar, 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 planar. Actually, this one is not planar. It's tetrahedral, but it has 2 groups that can reflect into each other. So if I cut the sheet of paper in half, the top half reflects into the bottom half because the molecule itself is planar.
Okay, thank you.
Yep. Because you were looking for like this way or this way or this way. Nice. What did you get, Matthew?
Like half a liter of this stuff. And then he's like quipping in the video. He's like, I don't know why there's so much in this procedure. It's like, bro, you didn't read it. Like,
Nailed it. Great work.
oh, okay.
Good work, Milena. What'd you get, James?
Okay, so I have a question. So these three, you want us to work on these three.
That's just those ones for now, yep.
So each of these structures could potentially have multiple chiral sites, right?
No,
No, wait, what?
this one does, and you did point out the chiral center. Here you've added hydrogens to these carbons, is that true? But that actually gives them 5 bonds.
Yeah, that was what I like to
So if, that's right. So if it was just those carbons that you were looking at being chiral, actually they're not, because they don't have 4 groups. They only have 3 groups.
Yeah, so only this.
That's right. Good work, Lamb. All right, structure number 1. Achiral. Where is the plane of symmetry? There must be one, because achiral means symmetric, so where's the plane of symmetry? Yeah, I mean, we could say, let's orient one of these CH3s up into the air, the other one down, and then we'll have the hydrogen that's there in the plane of the board. So if we can reflect the CH3s into each other, but then how do we get the rest of the molecule in? Well, actually, all of the rest of the molecule are planar atoms. They're all sp2 hybridized trigonal planar atoms, so they all exist in the plane of the paper. The plane of the paper is the plane of symmetry. The top half of that molecule is symmetric to the bottom half of that molecule. It's a flat molecule, other than those 2 methyl groups. But we knew that that carbon wasn't chiral, because 2 methyl groups are identical. It didn't have 4 groups. Second molecule? Achiral. Where's the plane of symmetry? It's the same. It's the plane of the board. And the last molecule? Chiral. There's only one chiral center here in the middle where the carbon is attached. It does have 2 carbonyl groups on either side, that chiral carbon, but one is a ketone functional group and one is an ester functional group, and those are not the same. Great. Let's talk about stereoisomers. These are isomers that take up space differently. So first, let's talk about enantiomers. Your hands are related as enantiomers, non-superimposable mirror images. That means that there is no rotation, no conformational change, no spinning or flipping that would allow these 2 molecules to ever superimpose. The quickest way that I like to identify enantiomers, all chiral centers flip. If I had wedge, wedge, dash, I need to have dash, dash, wedge in order to create an enantiomer. This is a relationship, so you can't ever look at one compound and say, oh, that's an enantiomer. You look at 2 compounds and relate them as enantiomers. Not every molecule has an enantiomer, because some molecules are superimposable with their mirror image. Anything that has achirality, anything that has symmetry, meso compounds and achiral compounds are symmetric with their mirror image, superimposable with their mirror image. So they do not have enantiomers. They don't exist. That relationship isn't there. Diastereomers, and I like that this starts with dia because there are 2 things that I look for. 2 compounds are diastereomers if at least one chiral center is different and at least one chiral center stays the same. This means that they are not mirror images, they're also still not superimposable. No rotation, no flipping, no conformational changes, no spinning allows for these two compounds to superimpose, but they are not mirror images of each other. All right, so I want you guys to go through that second line of compounds and see if you can relate them. Are they identical? Are they enantiomers? Are they diastereomers? Or does it not apply? And it might be good for you to go through and see if you can assign them as chiral, achiral, or meso compounds.
Are we saying if they're enantiomers or diastereomers?
That's right. Determine their relationship, or identical, or it doesn't apply. They're like, they have different chemical formulas.
Yeah, that's what I was saying. That's why I went like this. Yeah, so it's the same molecule.
Yeah, this one is a enantiomer, so it's the
This one I would say
Oh, I would
two possible carbons that are chiral.
Yes.
Like, how do you determine if a molecule is chiral? Or is it just looking at individual ones?
I erased it, dang it. But we said a chiral molecule has at least one chiral center. So if it has more than one, it might be chiral. But meso compounds have at least two chiral centers that are related by a plane of symmetry. They're symmetric to each other.
Okay, then this
So
so this first one's not.
the first one is not meso. That's right. It's actually achiral. And the relationship between them?
Enantiomer.
Well, they can't be, because meso compounds and achiral compounds don't have enantiomers.
So just not stereo. Oh.
They are
Not stereo.
identical.
Okay.
They're the same molecule flipped over like a pancake.
I see.
So if there's a conformation of this molecule where the two chiral centers can be symmetric to each other, then it's meso.
Right.
But if there's no conformation that reflects them, then the compound is chiral.
I see.
Yeah?
Yeah, thank you.
And that pH, phenyl, on one side and not on the other tells us they're never going to be symmetric to each other. There's never going to be a plane of symmetry reflecting those two chiral centers. So the molecule is chiral. Good. All right, what did you guys call the first pair? Identical. Is the molecule chiral or achiral? Is it meso? No, because there are no two chiral centers. In fact, there's not even one chiral center. So this molecule is related to the other molecule by flipping it like a pancake. And then it superimposes. So these are identical. What about the second set? Enantiomers. meaning the compounds must be chiral. How can we know that? No plane of symmetry, and there's only one chiral center. Meso compounds need to have two chiral centers reflected into each other. This doesn't even have that chance. Because there's only one plane of symmetry, one chiral center, if that chiral center changes, then all chiral centers have changed, and so the compounds would be related as enantiomers. What about on the bottom? What's their relationship? Diastereomers. Are either of the compounds meso? Those carbon chains are different. One side of the carbon chain has phenyl, the other has methyl. So even if you rotated into a new conformation to try and get those two OH groups to be both wedged or both dashed and look for symmetry, you'd never see symmetry between methyl and phenyl. So these compounds are both chiral. And because both are chiral and one chiral center has stayed the same, one has changed, they're related as diastereomers. All right. I also want to talk to you guys about regiochemistry. This is where all functional groups come into play, depending on what atoms are bonded in what ways. We get all of our different functional groups. How are you guys feeling on your functional groups? Good? Bad? Oh no, more people raised their hands after I said bad. Keep reviewing it, right? Keep studying them, keep practicing them. One of your first analysis assignments will come back to looking at IR and functional groups. So it'll give you a good chance to review them. But your first unit test next weekend also talks about functional groups. It has some questions on it. Some other ideas that we talk about with regiochemistry is degrees of substitution. This is where we refer to carbons as being methyl carbons, primary, secondary, tertiary, and quaternary. Now you can refer to a carbon by any of these terms, but you can also describe a functional group by the degree of substitution of the carbon it's attached to. One of these descriptors cannot be applied to a functional group. Can you tell me why?
Because then the carbon would be connected to 4 carbons.
Well said. The quaternary carbon describes a carbon bonded to 4 other carbons. It can't be bonded to 4 other carbons and another functional group, right? So this will never describe other functional groups, but these will. So I want you guys to go through this list and see that you can identify the carbons that are methyl, primary, secondary, and tertiary, and then more specifically, look for some of those functional groups. I do want to point out the difference between methyl and a methyl group. A methyl group is a CH3, sometimes connected to another carbon, which would make it a primary carbon because it's connected at one point. A methyl carbon, rather than a methyl group, a methyl carbon is not connected to any other carbons, okay? Primary and methyl, they get a little jumbled. So see if you can go through and label these regiochemistry terms. I'm going to draw these up and label them as well. Oh, I didn't draw that molecule right. Not quite. This carbon here is bonded to a magnesium and one carbon. So we'll describe it as primary.
Wait, so it has to be bonded with other carbon?
Right. All we use it for is describing the number of carbons it's bonded to. So this one's quaternary. That one's primary. Great.
So then this would be secondary.
Yes. Perfect.
Secondary. And this would, just be secondary as well.
Perfect.
Double bonds count? Like this also secondary or no?
You know what? I actually try to avoid that, but yeah, the regiochemistry I use is more substituted or less substituted. Well, I'll talk about that. They're not great for applying the same rules to, actually. Nice. Good work. Good review for you guys?
Mm-hmm. Yeah.
Good. All right. Lily.
Never mind. Okay, I just was wondering if you could repeat your definition for what you said.
Yeah. So a primary carbon is bonded to one other carbon.
Sorry, no, about the methyl and the methyl group.
Right. So this is a methyl group,
This right
Yeah.
here. Okay.
but it's bonded to another carbon.
Okay.
So it's a primary carbon. It's not a methyl carbon.
Okay.
It's a methyl group,
Okay.
but it's not a methyl carbon.
And then this one,
Mm-hmm.
this is connected to 3 other methyl groups.
Sure.
4 other methyl.
4 other carbons.
Uh-huh.
This one's not a methyl group.
Yeah, okay.
4 other carbons, so quaternary.
Okay.
This carbon is not bonded to any other carbons. So it's a methyl carbon.
Okay, thank you.
Yep. All right. Yes.
Are we labeling every carbon?
If you want to.
Just like
Specific ones. So I couldn't tell if you're trying to do like centric search, but you did the end.
Yeah. I was going for more like the functional group. Describe the functional group, but I think it's a good practice to label all of them. So that first compound you had is a methyl carbon. It's not bonded to any other carbons. We might call it a methyl group, but it's not a methyl group like we know it. It's not at the end of a chain. Here is a methyl group, 3 methyl groups in fact, but these methyl groups are actually primary carbons because they're bonded to one other carbon. That's the distinction and the confusion between a methyl group and a methyl carbon. Methyl group bonded to another carbon, methyl carbon not bonded to any other carbons. We actually see something similar when we use the term tert-butyl group. It's often a quaternary carbon that is connected as the tert-butyl group. Okay, methyl carbon up top. This is a primary alcohol. The alcohol is connected to a carbon that is connected to only one other carbon. So a primary alcohol. The carbon in the middle here is a quaternary carbon. I just wanted to point that one out. Here we have a secondary amine. You know what? This was a bad example because we use that term differently. I'll say this way. This amine is connected to a secondary carbon. A secondary amine would be connected to 2 carbons on its own. If we wanted to talk about the ketone, we could also describe that as a secondary carbon. The ketone carbon is bonded to 2 other carbons, so it's a secondary carbon. And then these methyl groups on the end, those are primaries. Here we have a tertiary carbocation. It's only connected to 3 other groups. If you connected a halide there or an alcohol or any other group, it stays a tertiary carbon but here we're describing it as a tertiary carbocation. And then we have our quaternary carbon down here. There are a couple of other compounds that I gave you guys. One of them was a benzene ring, a carbon coming off of it, and then a connection to this magnesium bromide. This is a different regio term that I want you to be aware of. This position off of the benzene ring we refer to as benzylic. And we'll be working with that a lot this semester, so it's a good chance for us to review it. This last structure, which has a tosylate group attached, OTS, this tosylate is positioned allylic. There's another term, vinylic, which describes being attached directly to the alkene. So if we were to describe these hydrogens attached, we describe them as vinylic. So being attached directly next to the alkene, attached directly to the alkene carbon versus attached to the position adjacent to the alkene, we give different regio terms. I do want you to see this relationship between benzylic and allylic. It's one away from that carbon-carbon bond. Just depends on whether it's an alkene or a benzene ring. All right. So I think we'll totally have time to get through all the reactions on this sheet today. Oh man, isn't it crazy how long these sheets can take? Anyways, there's, I think what I want to end with today is one last different terminology. It's not on this worksheet, and that is degrees of unsaturation. Good time to review it since we're talking about degree of substitution. Unsaturation describes how a molecule could have more atoms attached. It's not fully saturated with atoms. It is unsaturated. And we can calculate unsaturation using the two-chicken rule. If you take twice the number of carbons in the chemical formula, subtract the hydrogens in the chemical formula, subtract the halogens, add the number of nitrogens, add 2, and then divide by 2, you can calculate how unsaturated the molecule is. And I call this two-chicken because you multiply by 2, you divide by 2, you add a 2, you subtract 2 times, you add 2 times, and it spells chicken. So this is useful if you have a chemical formula. If you're working with a structure, degrees of unsaturation come from pi bonds and from rings. Every ring creates a degree of unsaturation. Every time a molecule connects back in on itself, it's shortchanging itself from connecting to other things. It's unsaturated. And every time 2 atoms connect to each other more than once, they're shortchanging themselves on how many other things they could be connected to. So degrees of unsaturation is a useful tool for us to use to communicate about what reactions are possible with different compounds. All right, have a good weekend. I'll see you guys on Monday, and we'll get into our chemistry, the real reactions.